If you look back at the edge of a black hole, you'll see 100 versions of yourself. This isn't magic, it's a photon sphere. After 15 seconds, even light can't escape your eyes. Today, let's talk about a hardcore topic. What happens if you're thrown into a black hole? This isn't science fiction. This is a speculation based on hardcore physics. Before throwing you in, let's briefly review what a black hole actually is. Even the old man Einstein once described it as the place where God divides by zero. He didn't believe this thing could actually exist in our universe. But look, humans really did discover it. When those especially massive and dense stars reach the end of their life, they undergo a massive transformation. They collapse into themselves, leaving nothing behind. What they create is called a singularity, a mysterious point in space-time said to have infinite density, and therefore infinite gravity. General relativity gave us a revolutionary idea. Gravity is not a force acting on objects. It's the result of space-time curving due to mass. A pure curvature effect. It completely explains how Earth orbits around the Sun, and how all the planets revolve like circling their home. They spin. There's no solid black surface inside a black hole. The singularity hidden inside is just incredibly dense, so much so that it severely warps space-time, forming a deep well with vertical walls. In 1939, Einstein himself published a paper specifically stating that it's unreliable to think stars collapse into singularities, and it wouldn't happen in our universe. But ironically, in that same year, Oppenheimer, yes, the famous Oppenheimer, along with physicist Snyder, co-authored a paper predicting that stars really could collapse under their own gravity and become a black hole. Now let's talk about what happens if we throw you into a black hole. The most amazing thing about black holes is anything can become one. Whether you're a star, a planet, or a little person like us, as long as you're compressed within the Schwarzschild radius, you can become a black hole. German physicist Carl Schwarzschild was the first to solve Einstein's field equations exactly, and what he found was both simple and beautiful. Take our sun, for example. If you compress all of its mass into a sphere with a radius of just 3 kilometers, it would become a black hole. What about Earth? It would have to be compressed into a sphere with a radius of about 9 millimeters, basically the size of a marble. If a human wanted to become a black hole, that would be tragic.
Take our sun, for example.
You'd have to be compressed to much smaller than a proton, unbelievably small. But if you could really become that small, then you'd be a black hole too. So, which black hole should we throw you into? I think it's time to drop you into one. But which one should we choose? We could pick a small one, but that's no fun.
You would be a black
Let's
hole
go with a
too.
bigger one. Some black holes have event horizons larger than our entire solar system. They can contain billions of solar masses. But that might be too extreme. Why not pick one a bit closer to home? Sagittarius A, the supermassive black hole at the center of our galaxy. You're orbiting around it right now, and it's also one of the only 2 black holes humans have ever imaged. Now let's set the scene. Suppose you and I fly there and park the spaceship about 1 trillion meters from the event horizon. How do we get you into the black hole? As you begin to fall freely, I'll stay on the spaceship to observe. But here's the key. General relativity tells us that people near a black hole might experience time completely differently from others. Because black holes warp space-time so intensely. This effect was shown in the movie Interstellar. To track time, we'll give you a special watch. It can show how much time has passed from both your perspective and mine on the ship. Each view tracked separately. Let's sync the watches and your journey into the black hole can begin. As your journey starts, you'll see the black hole devouring matter in the distance. The scene is absolutely spectacular. Friction heats the matter to extreme temperatures. If you tried to simulate that scene on a regular laptop, it would take over a decade. In reality, the accretion disk would glow bright blue or even white. But in this simulation, it's rendered orange to make it easier for us to observe. When you first check your watch, only 30 minutes have passed, and you've only completed 0.1% of the journey to the event horizon. So far, I've only experienced 11 more seconds than you on the ship. The time difference isn't too dramatic yet. Now that we're closer to the black hole, the space-time around it is so warped that it's creating all sorts of strange visual effects. Light from the sides or even the back of the black hole is bending before it reaches your eyes. Let's check the time again. You've now been falling for 2 hours and you've completed 1.4% of the journey. And now I'm 44 seconds ahead of you on the ship. The time gap is starting to get concerning, but it's still not outrageous yet. The black hole's shadow, that dark region in the center, seems to be growing faster than expected. That's due to gravitational lensing, which bends light that would have passed by you right onto your retina. And now a long time has passed again. You finally check your watch again, and what you see is shocking. From your perspective, you left about 12 hours ago, but for me on the spaceship, I've been watching you drift toward the black hole for nearly 15.5 hours. We are now very close to the black hole, and things are about to get extremely strange. Before you reach the singularity, you'll enter a strange and magical place. If you were frozen in this special region in time and looked around you, you'd be amazed at what you see. You've reached the Photon sphere, one of the most bizarre places known in the universe. In the photon sphere, gravity is precisely balanced so that photons can orbit the black hole. It's not light emitted or reflected by matter. The photons themselves are trapped in orbit. If the light is moving tangentially to the black hole, it can orbit around it. But if the path changes even slightly, the photon either falls into the black hole or escapes into space. Under these specific conditions, if you were frozen right at the photon sphere and looked around, you'd see a mirror image of yourself facing away. You'd see multiple copies of the back of your own head staring into space. You're actually seeing yourself, as if you're standing beside yourself. And you don't need any tech to achieve it. It's all thanks to the warping of space-time itself. As your journey continues, you're now getting very close to the event horizon. You've passed the photon sphere. The black hole now dominates your entire view. It feels like you're being swallowed by darkness. That's because the darkness is bending around you, showing you the backside and sides of the black hole's shadow, along with the parts that would normally be visible in flat space-time. You've now been falling for 13 hours. In another 24 minutes, you'll reach the event horizon. But from the spaceship, I've been watching your journey for almost 20 hours now. Another 18 minutes pass, you check your watch again. Now I've observed you for almost 40 hours. Those last 18 minutes for you lasted 18 full hours for me. The final moment has come. In 6 more minutes, you'll cross the event horizon of the black hole. You close your eyes, take a deep breath, and check your watch. But something seems off. It shows that I've been watching your fall for an infinite amount of time. But it's not broken. That's just how physics works. I spent decades aboard the ship, watching you slowly approach the event horizon. Eventually, I see you turn red, which means I can only see you using infrared telescopes. I will never see you cross the event horizon, even if I live forever. For you, those last 6 minutes lasted an eternity for me on the ship. It sounds like science fiction, like a daydream, but it's absolutely real. It comes directly from Einstein's equations. Now you've entered the event horizon. So what happens inside a black hole? Strangely, you may not even notice the exact moment you cross the boundary. You can still look outward at the universe, see distant stars, even see our spaceship floating in space. But all of that light, like you, is also heading toward the singularity. You've passed the singularity, the point of infinite density. All our physical laws break down. Time stops. To escape the singularity's gravity, you'd have to go faster than light, which we know is impossible. There's a common misconception that if you looked outward from inside, the extreme time dilation would let you see the entire future of the universe. History unfolding before your eyes, but that's not true. Because of relativity, as you approach the singularity, you'll see the universe compressed into a narrow ring. Eventually, as you get close enough to the singularity, your feet will be stretched ahead of you, your body elongated, a process called spaghettification. You become one with the black hole, drifting through the cosmos for eternity. The very thought sends chills down your spine, yet you can't help but be curious. Black holes, these mysterious celestial bodies, fill us with awe and fear at the same time.